Good morning, everybody, and welcome to the second day of the Attochem annual meeting, second annual meeting. So today we have a session on Attosecond spectroscopy in polyatomic molecules, and we are welcoming three speakers. We will start in 1 minute. I just remind you that for asking questions, you should use the live question and answer tab on the application and write them even through the presentation, and we will handle all the questions at the end of the talk. So our first speaker for today, very welcome, is Yann Meres from Celia Bordeaux, and he will present about chiral sensitivity of tunnel ionization dynamics. So thank you, Jan. The stage is all yours.
Thank you for the introduction. Welcome, everyone. So first, I'd like to thank the organizers for inviting me to present these results. And so I'm going to talk to you about a joint experimental and theoretical investigation that we have undertaken in the past 3 or 4 years at Celia in Bordeaux, in close collaboration with the Weizmann Institute in Israel and LCPMR in Paris. So the goal of this investigation is to unravel the possible influence of molecular chirality on tunnel ionization dynamics. So I will talk about strong field processes. And as you know, strong field processes are used for many applications in molecular imaging. There are different techniques which are used. When you take a strong laser field and send it on molecules, there can be different processes occurring. There are electrons which are ionized before the maxima of the field, and these electrons are drift away and are accelerated and form above threshold ionization peaks. Now, some of the electrons are going to come back and experience rescattering close to the ionic core, and these two can interfere, producing holographic patterns. Now, electrons can also rescatter and gain a lot of kinetic energy, reaching 10 UP energies. Or the electrons can also recombine and emit harmonic generation. So all of these processes can be used to do what is called self-imaging of a molecule and, for example, reviewed in this paper. Now, the primary process common to all of these studies is tunnel ionization. And so we can describe it as a two-step process where first we have an electron wave packet which is going to tunnel through the potential barrier lowered by the laser field. And so this is really the tunneling process with sub-barrier dynamics. And then once the electron is freed, it's going to be accelerated during a post-tunneling dynamics in the continuum. So the laser field accelerates it. And so the question I would like to address today is the structural sensitivity of this process. So in general, we use a lot the strong field approximation. And in the strong field approximation, we state that the electron, once it's here in the continuum, it doesn't feel the ionic potential at all. There can be corrections brought to this strong field approximation, Coulomb-corrected SFA, in which you take into account the influence of the ionic core on the electron trajectories. And you can also actually do sub-barrier Coulomb-corrected SFA. And it was shown that there is actually an additional phase shift here of the emerging wave packet, which is imprinted under the barrier during the tunneling. And this is, for example, discussed in these papers. So if you want to probe the structural sensitivity of tunnel ionization, we need a signature of the interaction with the potential. And the idea that we proposed here is to get this unambiguous signature is to use two ingredients. First, our target is going to be chiral molecules, and the laser field which we ionize the molecules with is going to be rotating in time. So why is this interesting? Because there's when you ionize chiral molecules with a rotating laser field, you get a very strong signature of the potential in the ionization signal. So very briefly, chiral molecules exist as two forms, which are called enantiomers, and so they are mirror images, but they are not superimposable. Our signal in all the experiments is going to be based on the photoelectron circular dichroism process. So here's a sketch of the typical experiment. We have randomly oriented enantiopure chiral molecules in a jet, and we ionize them with a laser pulse, for example, circularly polarized. We collect the electrons which are ejected. Here we accelerate the electrons with electrodes onto a detector to do velocity map imaging. And so the idea is that the electrons have a 3D angular distribution, and we project this 3D distribution onto a set of microchannel plates, a phosphor screen, and a CCD or CMOS camera. So what we measure is the projection of the angular distribution of the photoelectron spectrum. Now, what happens when the field is circularly polarized and the molecules are chiral is the photoelectron circular dichroism effect. It is very intuitively similar to what happens when you rotate a nut on a bolt. So if you take, for example, left-handed polarized light and you shoot a certain enantiomer, you will monitor on your detector that there are more electrons ejected forward than backward. In other words, the rotation of the laser field induces a translation of the electron distribution in the chiral potential in the same manner as when you rotate a nut on a bolt, the thread converts the rotation motion into a translation. Now, if you reverse the rotation direction, you know that the nut is going to go backwards, and it's the same with the electrons. If you now use right-handed polarization, more electrons are going to go backward than forward. So this asymmetry here is our PECD signal, photoelectron circular dichroism signal, which is commonly defined as a normalized quantity. And so it's plot here, for example, it's an asymmetry with respect to the light propagation direction. We will measure, for example, more electrons forward than backward. So what is interesting is that this is a pure electric dipole effect, and so it's a very strong dichroism, up to several tenths of %. And so this is what we will base the sensitivity of our measurements on. We are going to monitor forward-backward asymmetries in signals, in photoelectron angular distributions, and this will be the signature of the chirality. Why is this the signature of chirality? Well, actually, the asymmetry in the electron ejection really emerges from the scattering phases of the outgoing electrons in the chiral potential. And so this is a quantum mechanical picture, but interestingly, you can even describe PECD purely classically. If you take a chiral potential and you send electrons in the potential, and in a rotating laser field, you calculate the classical trajectories, and you do statistics with CTMC, you're going to find that more electrons are ejected forward than backward, even if you average over random orientations of the molecules. So what about now strong field approximation, strong field ionization? So in the strong field approximation, as was shown in this paper, there is no photoelectron circular dichroism. You neglect the influence of the potential, thus there's no chiral imprint. So the most obvious thing is to state that when the electron is here accelerated in a continuum, it is going to feel a residual influence of the core potential and of the chiral potential, and this can imprint a phase and amplitude asymmetry in the photoelectron angular distribution. And so this is enough to produce a dichroism. However, one may wonder if the electron emerges far from the core, the chiral part of the potential will have vanished because we are very far away. So asymptotically, the potential is like isotropic. And so one may wonder if in such conditions, there would still be a PECD, basically an influence of chirality on the wave packet under the barrier, and such that there would be a PECD accumulated in this first step of tunneling. So we want to measure strong field ionization dynamics, and we're going to use the tools developed in Attosecond spectroscopy in the past years. So the main tools to measure strong field ionization dynamics are rabbit-like measurements, and yesterday we heard about several rabbit experiments, attoclock measurements, and photoelectron interferometry. So how can this be used? It was shown, for example, that yesterday we saw rabbit with an attosecond pulse train in the XUV, but you can also do rabbit-like measurement using strong field ionization and access photoionization delays. The attoclock is a bit of a different scheme where you use the angular streaking by a rotating laser field, and it's been applied, demonstrated first on atoms, and I will really discuss this in more details later. And last, if you want to measure more information on the strong field ionization dynamics, you can do photoelectron interferometry, because then you can measure relative phase between different wave packets, and you can actually reveal that there is a subbarrier phase, and as was shown in atoms. So what about chiral molecules? Well, the rabbit-like measurements were done in chiral molecules, and we demonstrated that the photoionization delays were sensitive to chirality. There is a delay of a few attoseconds to a few tenths of attoseconds between two mirror images of a molecule. Attoclock measurements were recently done by the Frankfurt group in chiral molecules, and they demonstrated that there was a forward-backward asymmetry of the angular streaking by a rotating laser field. And regarding photoelectron interferometry, well, one issue is that in general, you do this interferometry using linearly polarized fields, because if you use circularly polarized field, most of the interference structures vanish. So that could be a problem for chirality, but we'll see how it can be solved. So this is the outline of my talk. We made two studies to reveal the influence of chirality in tunneling. Chiral attoclock measurements and subcycle gated chiral photoelectron interferometry. And today I will focus here on the first part. So just to let the chairman know that it's normal that I'm going to be very late on schedule if I had the second part to present. So I will first discuss the principle of the attoclock measurements. The idea is to photoionize a target by an elliptically polarized laser field. So this is the laser field which points in one direction here at certain time t0, and then the laser field is going to rotate in time. Now, when the laser field is maximum, it can there's the highest probability to ionize electrons, and so there's a wave packet schematized here. And once this wave packet has emerged, it's going to be angularly streaked by the rotation of the laser field. And so in time, the wave packet is going to rotate. Now, if you measure the final momentum distribution of the wave packet, you observe within this simple picture that the angular distribution is going to maximize along the direction orthogonal to the laser field at the time of ionization. And this is actually derived very easily in the strong field approximation. The final momentum of the electron is the opposite of the vector potential at the time of ionization. So if you measure the photoelectron angular distribution, it's going to point in one direction, which gives you information on the ionization dynamics. So one way to see this is that if the electron was taking a certain time, or if it takes a certain time to go through the potential barrier, then basically when it emerges, the laser field does not point around the vertical direction, but has a certain offset here. So your electron distribution does not point along the x-axis, but is rotated by a streaking angle, which is related to the attoclock delay. There is another way you can observe such offsets of the attoclock distribution, is if the electron actually tunnels out at t0, but then during its acceleration, the influence of the ionic potential can induce additional rotation of the angular distribution. And in that case, you are also going to measure an attoclock delay or an attoclock streaking angle here, offset. So this was extensively studied in the past few years, and the dominant effect in general is this one. The influence of the ionic potential really induces large streakings on the attoclock distribution. So we keep this in mind for the following. Now, in our experiment, we will use an attoclock with bicircular fields. So instead of using an elliptical laser field, we're going to use a combination of fundamental and second harmonic fields, which are both circularly polarized, and in which we can define an helicity here, relative helicity. So the two fields are either be co-rotating or counter-rotating with a certain helicity. This is the intensity ratio between the two fields R. So, I mean, these bicircular fields are really versatile tools from strong field interactions. They are used in a growing number of experiments. And in our case, we are going to use co-rotating fields, actually. This is the equation for co-rotating fields. So what does the field shape look like? This was the elliptical case. This is an elliptical field, elliptical vector potential. And in our case, we'll have this configuration. So the field is sort of heart-shaped, and the vector potential maximized here along the horizontal direction. There's been a few theoretical studies which have shown that bicircular fields could be used for attoclock, mostly in the counter-rotating configuration, but here we will use co-rotating configuration to avoid interference effects. So the principle is exactly like the Attosecond I showed before. We use this field here to ionize the target. The electrons are going to emerge in one direction, be angularly strict, and be detected maximizing along a given direction. This is our experimental setup. So these experiments were done using a 1 kHz TISAF laser system. We split the incoming laser beam in two parts in a Mach-Zehnder interferometer. And we have here wave plates on each arm, the 2 omega, the second harmonic and the fundamental, such that we can actually control the fields to get them co-rotating or counter-rotating. The target molecules are going to be camphor and fenchon. So you just have to keep in mind that they have quite low ionization potentials compared to the targets we generally use in strong fields. They have an IP of 8.5, 8.7 electron volts. And these two molecules are isomers. They differ by the position of the two methyl groups here. And so it's a good test of the structural sensitivity of our measurement. And the detector will use velocity map imaging. And as I told you, the VMI measures the projection of the 3D distribution. But to get Attosecond measurements, we need to retrieve the full 3D distribution. And so we will use a tomographic reconstruction. We are going to basically rotate the distribution and record projection for 31 angles, and then retrieve the 3D distribution. So this is the experimental results. The photoelectron angular distribution we measured in camphor molecules. So the geometry is here, the propagation axis is Z, and we are here in the PX, PY plane, which means we sit in the laser polarization plane. So we have different above threshold ionization peaks, and you see that they maximize along different streaking angles. This is really the plane of the Attosecond. So the Attosecond angle phi 0 depends on the ATI order, so it depends on the energy of the electron. Now, we want to resolve the Carroll response, so we want to compare this angle for electrons ejected forward at positive PZ or backwards at negative PZ. So we are going to characterize this as a function of an ejection angle theta. So forward electrons have positive theta, backwards electrons have negative theta. And we're going to resolve this angle here for each ejection angle of the electron. So this is the results. We have here electrons ejected forward, electrons ejected backward. And for each ATI peak here, we measure the angle maximizing the distribution. So what we observe, these are electrons ejected in the polarization plane. We see that there is an offset between the first ATI peak and high ATI peaks, and this offset is about 50 degrees. As we move away from the polarization plane, we go back forward, we see that there is a shift of the Attosecond. And if we go backwards, there's also a shift, but by a different quantity. You see that this value here is clearly different from this value here. So there is a forward-backward asymmetry, and this is the signature of chirality. So what we do is we extract the differential angle between forward and backward emission, and we plot it here. So this is really the Carroll-Attosecond asymmetry. We see that for the first ATI peak, it reaches very large values. And after this, the other ATI peaks have similar behaviors. There's with a shift which reaches about 2 or 3 degrees between forward and backward electrons. So this is the first signature of the chirality, of the influence of chirality in the electron ejection dynamics. But there is another thing we can look at, which is actually the asymmetry in the number of ejected electrons. This is the primary process of photoelectron dichroism. There's an asymmetry in the number of ejected electrons. And so we calculate this asymmetry and we plot it here. So this is really what I would call here the Carroll asymmetric yield. There are more electrons ejected forward or backward. And so we see that this map is interesting. The first ATI peak shows the different behaviors from the other as on the other quantities. But then what is remarkable is that we see that this asymmetry increases with the kinetic energy of the electron. This is ATI 2, 3, 4, 5. And so for the highest ATI peak, we measure the strongest asymmetry, reaching about 2% here for this angle. And this is somehow counterintuitive because generally the Carroll sensitivity decreases with kinetic energy. High kinetic energy electrons are less sensitive to the structure of the potential. So, well, this could be basically just due to the specific structure of the molecule. So we wondered how general is this? We repeated the measurements in Fenton molecules. So we see that the behavior is really similar. For example, for the first quantity, you see I blink between the two, we get something very similar. Now for the forward-backward asymmetry in the streaking angle, we get weaker response. Sorry for the blinking. You see this goes to 4%, this goes to 2%. So we get a weaker chiral response. And actually for higher order ATIs, it's almost zero. And we get a weaker also asymmetry in the electron signal, which reaches only less than 1%. But the trend is the same. You see that apart from the first ATI peak, which is always different, the higher order ATI peaks see their asymmetry increasing with the order. So remarkably, for the high energy electrons, we have no chiral out-of-clock shift, but we have a strong asymmetry in the electron yield. So to interpret this, we'd like to decouple the influence of the two steps under the barrier and continuum in the out-of-clock. And this was nicely done, beautifully done by Lisa Turlina and coworkers a few years ago on atomic ionization. They compared the response from a Coulombic potential in black and a screened potential in blue, in which the Yukawa term is introduced to completely cancel out the long-range potential. And what they found is that if you use the full potential, you have an out-of-clock streaking angle, but if you screen the potential, there is no more out-of-clock shift. So this demonstrated that the out-of-clock shift is a long-range effect. Now, what about chirality? So our colleagues Bernard Ponce and Sylvain Larocque did calculations using the Bernardine molecule, which is a homemade molecule consisting of 4 atoms and 1 electron. And they used either a full potential or a screened Yukawa potential around the molecule. So let's see with the photoelectron angular distribution. You see that this is the measurements in camphor, Fenton, and the TDSE. The results are qualitatively similar, which means that this 4-atom molecule is somehow realistic. Now, if they screen the chiral part of if they screen the long-range potential, you see that the out-of-clock angles vanish, as was seen before in atoms. So then what we do is we're going to study the chiral response using, for example, the full potential. So this is the out-of-clock shift, which is rather similar to the experiment. This is the chiral out-of-clock asymmetry, which is again similar to what was measured. And this is the chiral asymmetric yield. And again, as in the experiment, we see that high order ATI peaks are more asymmetric. Now, what happens if we screen the potential? This is the out-of-clock shift, which vanishes. So it's canceled by the screening. Now, the chiral part of the potential of the out-of-clock response is also canceled, but only for high enough ATI orders. So you see that basically the screening is not very efficient for low energy electrons, but as you reach ATI 4, the screening completely acts. Now, very remarkably, if you look at the asymmetric yield, you still see a very strong asymmetric yield in the screen potential. So there is no chiral out-of-clock delay, but there is a strong asymmetry in the number of ejected electrons forward and backward, especially for high energy electrons. And so what this tells us is that since we have no out-of-clock chiral asymmetry, the potential is really canceled. The chirality of the potential is really canceled in step 2. But we still measure a strong asymmetry in the electron yield, which leads us to conclude that this results from the pure tunneling dynamics. So the subbarrier dynamics can induce a chiral response as an amplitude asymmetry at the exit of the tunnel. And so it means it's imprinted under the barrier by the chiral potential. So this is the conclusion of this out-of-clock study. Now, very briefly, we also wondered about the phase which could be imprinted during the subbarrier dynamics. And this is the second part of the work, which I just briefly mentioned here, the subcycle gated chiral interferometry. So if you want to measure phase properties of the wave packet, you want to do interferometry. And we know that, for example, orthogonal two-color laser fields are very good candidates to observe double-slit interference in ionization. And so these orthogonal two-color laser fields show a complex shape, for example, describe an H shape as a function of time. And so this is really the scheme we used in our experiment and theoretical study. Now, the rotation of the electric field can induce chiral responses, as we have shown a few years ago. And this is, for example, the chiral response measured using this orthogonal field. And using this scheme, the result is that we showed that the ionization dynamics could induce not only an amplitude modulation of the ATI peaks, but also a phase modulation of the ATI peaks. So we observed a 20 milliradians chiral phase shift and a 2% amplitude modulation, which is accumulated during tunneling. So here are my conclusions. Our study shows that the subbarrier dynamics can induce a chiral optical response. In the attoclock, we saw no chiral tunneling delay, but we saw a chiral subbarrier amplitude modulation. And in the interferometric study, we measured also, we observed also phase modulation. So you could wonder how can an instantaneous process be sensitive to the rotation of the field, which is something which happens in time. And this apparent contradiction can be resolved by going to the complex plane, because there is actually a dynamics along the imaginary time axis. Now, I pointed that all of this was done in the non-adiabatic tunneling regime, in which actually the electron can get excited before tunneling, and this could imprint some chiral sensitivity. So the question of what would happen in the pure adiabatic tunneling remains open, and we believe that there should be a PECD. And just as a final conclusion, I would like to stress the generality of the effect of chirality in strong fields, which was a bit surprising to me, because actually chirality plays a role in all steps of the process, from subbarrier dynamics. It can also induce additional effects in Coulomb-focused electrons. We recently measured a very strong signature of chirality in backscattered electrons up to 10 UP, and in the recombination process, it can affect chiral harmonic generation. And the Ottawa U group recently shown that it also affected strongly non-sequential double ionization. So basically, chirality can play a role everywhere in strong fields. I'm done. Sorry for the minute delay. Thank you.
Thank you, Jan. Thank you for this very nice talk. So I'll have a check to the question and answer. So please go ahead with questions if you have from the audience. You are also very welcome to switch on your camera so that we can see and we can. And while we are waiting for people to jump in, I may have a couple of questions. One is maybe I missed a little bit of the discussion. I didn't understand exactly, I mean, which is the argument, why these high kinetic energy electrons are more sensitive to the potential with respect to the low energy ones.
So
counterintuitive, as you said, but it didn't
exactly.
Why is that? Is like
so
that?
Well, the reason why I don't know. What I can say is that this is clearly an observation both in the experiment and in the calculation. And usually we tend to think that they will be less sensitive because we think in terms of scattering of the outgoing electron in the potential, right? But what we are saying here is that using the screening, we have killed the influence of the scattering in the continuum. So what we're left with is a pure subbarrier dynamics. And then the influence of the kinetic energy of the electron is actually mostly due to the time of ionization, you know, because the electron is actually tunneling. So this is really a subbarrier process, which we would have to investigate further, but it's due, I guess, to the different ionization times of these electrons. And so the barrier dynamics is different for different energy, final kinetic energy of the electrons.
I see. Okay, thank you. Well, that makes sense. Let's see if we have some question popping up from the audience. I don't see any. So I can go ahead with one is a very, let's say, specific questions on the experiment, in the sense that you said that you did this tomographic reconstruction on the VMI images with a 1 kHz laser. So I was wondering how much time would it take to complete the full reconstruction for like the...
Yeah, so to record the full 3D measurements for both polarization it was taking, I would say, between 4 and 6 hours. And so since then, we've done measurements with the higher rep rate system. And of course, yeah, now when we do VMI tomography of PECD, it takes us a few, like 10 minutes typically. Yeah.
Wow. Okay. Yeah, that's very nice. So we have a question from Carlo Callegari. I don't know if he wants to switch on his camera. Anyway, I'll read the question. Higher kinetic energy also corresponds to higher angular momentum. Have you considered that?
I would say no. We haven't taken this into account. Again, so the question is really about what happens during the tunneling and what is acquired during acceleration and interaction, further interaction with the field. And so this relates to the question of the angular momentum distribution of the electron emerging from the tunnel somehow. And in other words, it also relates to the question of the momentum distribution and angular momentum distribution of the electron emerging from the tunnel. And this is really something that obviously plays an important role and through which the chiral asymmetry imprints. But I haven't more specifically looked at this. It's an interesting point.
Well, thank you. I think now we can go ahead with the next speaker. Thank you again, Jan, for your presentation and the discussion. So we may move to the second presentation of today from Davide Faccialà from CNR in Milano. He will be discussing probing ultrafast chiral dynamics in complex molecules with chemical sensitivity. Please, Davide, go ahead.
Thank you, Caterina, for the introduction, and good morning, everybody. First of all, I'd like to thank the organizers, too, for giving me the opportunity to present our results at this workshop. So I'm a postdoc at CNR, working in the ultrafast dynamics in matter group in Milano. And today I present the results of an experiment where we probed ultrafast chiral dynamics in a complex molecule with chemical sensitivity. So I'll start with outlining the main motivation of our work, where we combined potentialities of time-resolved photoelectron circular dichroism and core-level photoelectron spectroscopy to probe the relaxation dynamics of a complex molecule with site selectiveness. I'll then present the approach and palm probe method of our experiment that was performed at Fermi FEL in Trieste. And I present the main experimental results in the static and dynamic, that means palm probe regime, and that end with some conclusion. So as you all know, chirality plays a fundamental role in nature. Chiral molecules are non-superimposable to their mirror images. And while showing the same physical and chemical properties, their interaction with another chiral object changes dramatically between the two enantiomers. And a remarkable example is the one pictured here, methamphetamine, that is normally used as a harmless vasoconstrictor drug in its level rotatory form depicted in left here, while it produces euphoria and addiction in its dextrorotatory form. And the enantiospecific properties of a chiral molecule can be probed with a technique that I already introduced Jan, which is photoelectron circular dichroism, or PECD, that, as already said, is more sensitive to the chirality compared to conventional circular dichroism. And just to briefly summarize, this technique consists in inducing photoionization first with a circularly polarized light from a sample of randomly oriented and pure enantiomers, and then collect the photoelectrons emitted from the sample. And the chirality emerges from the forward-backward asymmetry in the angular distribution along the propagation axis of the laser. And this asymmetry reverses in Ellicity when the radiation is flipped. Then the photoelectron distribution can be measured with various techniques, and the forward-backward asymmetry is mapped in the odd coefficients of the Legendre polynomial expansion of the photoelectron angular distribution. In particular, when we have only the coefficient B1 different from 0 among all the odd coefficients, PECD is just defined as 2 times B1. Recently, PECD has enabled Combi and co-workers to study the relaxation dynamics of a photoexcited function enantiomer in a time-resolved manner. In this work, a 200 nanometer pump pulse excites the molecule from its ground state to the 3s Rydberg state. And after that, 400 nanometer circularly polarized probe photoionizes the system, producing the emission of electrons that are collected with a velocity map imaging spectrometer. And the PCD here arises from the chirality of the initial photoexcited state, the 3s Rydberg state, that basically projects into the outgoing electron wave function. And in particular, they found two main processes, one occurring in the first 400 femtosecond that have been suggested to be due to the intramolecular vibrational relaxation, and the other one on the picosecond time scale that instead was attributed to the internal conversion towards lower valence states. PCD also arises when we photoionize the system from a core level of a molecule. And in this work, Ulrich and co-workers observed a giant chiral asymmetry in the angular distribution of the photoelectrons that were ejected from the carbonyl C1s orbital of the function molecule. This orbital is here represented in blue. So in this case, the electron is emitted from an almost fully achiral state, this 1s orbital. And then the dichroism arises from the scattering of the electron through the surrounding chiral molecular potential. So the measured chirality is expected in this case to change depending on which point of the molecule the outgoing electron has been ionized from, basically allowing an in situ characterization of the chirality of the system. By using an ionizing pulse at 300 eV, they observed a forward-backward PECD asymmetry of about minus 18%. Remember, PECD is 2 times this coefficient. So here B1 is around 9%, and we have a PECD which is about minus 18%. In correspondence of this weak peak that is associated to the electrons emitted from the carbonyl carbon 1s state. While for the stronger peak here, that is associated to all the electrons coming from all the other carbons in the system, a weaker PECD is observed and with opposite sign. So what we did in our experiment was to try to combine these two techniques. So try to combine time-resolved PECD with the potentialities provided by a core level spectroscopy. An experiment performed at LCLS that combines these two techniques has been recently reported, and in particular in this work, Hilken and co-workers probed the core level PECD of an ionic chiral fragment during a photolysis. However, the low PCD of the target, that in this case is about 2%, and the difficulty of this kind of measurements have prevented to extract a clear pump probe dynamics at different pump probe delays. And in this perspective, function molecule, which I have already introduced, is a perfect candidate for this type of experiments. So why so? Well, this is due to the high asymmetry measured in the static PCD that I have already anticipated of the photoelectron coming from the carbonized C1s state, which is around -18%. And moreover, there's this interesting relaxation dynamics of photoexcited chiral function. And these dynamics triggered us to investigate if it could be possible to study these dynamics with site selectiveness. So in our setup, we used a 400 nanometer pulse to photoexcite the molecule from the ground state to the excited Rydberg state by resonant to photon absorption. And then we ionize the system with 300 eV circularly polarized pulse, switching between left and right circularly polarized light. The photoelectrons are then detected with a velocity map imaging spectrometer, and then PECD is measured. We performed the experiment at the Fermi Free Electron Laser FEL facility in Trieste, which is the first seeded free electron laser generating intense and highly coherent radiation in the extreme ultraviolet range, and allowing also to easily control the pulse polarization. In particular, the seed scheme of Fermi allows to couple FEL and pump laser pulses with an unprecedented time jitter as low as 6 femtoseconds on the sample. The experiment was performed at the low-density matter beamline that also provides a very versatile end station for gas phase experiments with multiple detectors, adaptive mirrors for focusing flexibility, and particularly a laser pump available at 400 nanometer. So initially, we performed a static study of PECD offension with our FEL source. As you can see here, the experimental PECD shows 2 peaks, and the weaker one is associated to the carbonized C1s state. So the electrons emitted from this carbon atom in orange, while the stronger peak is associated to the electrons emitted from all the other carbons that are the ones in green. And the experimental PCD is shown here in the plot below. These two results are compared with theoretical calculations based on 2 approaches. We used the continuum multiple scattering model with a Slater X-alpha local exchange approximation calculations performed by Ivan Povis to detect the chirality of all the contributions, and also combine these results with TDDFT for the binding energies. And it is possible to observe already a good agreement between the experiment and the theory, in particular in correspondence of the C1 peak, PECD of minus 18% is measured, while for the main C peak here, we have a PECD of approximately 2.5%. So these results that have been obtained with an FEL radiation are shown with squares in these 2 plots, and compared with the theoretical calculations shown with lines for the 2 enantiomers. And also for the C1 contribution, we can also compare this result with previously synchrotron data, which are represented by these orange dots. And we observe that we have a good agreement both with the theory and also with the previous synchrotron experiment. So the good match of these results performed with an FEL source demonstrate the possibility to probe the core level dichroism with a short pulse source. And so it allows to implement a pump probe approach for time resolved spectroscopy. So, as we said in our setup, we pre-excite the system with a 400 nanometer source. A 2-photon absorption matches with a transition from the HOMO state to the LUMO +1 state, the 3S Rydberg state. And the calculations performed with TDDFT show a change in the photoelectron spectrum from this excited state with respect to the ground state. In particular, we can observe that the C1 peak in red shifts to higher binding energy. And also for the two carbons C2 and C3 contributions that are the one linked to the main the carbonyl atom, and that are represented here in yellow. We have that also these two contributions shift to higher energy in the excited Rydberg molecule, overlapping basically to the binding energy of the C1 contribution in the ground state. All the other sites, all the other binding energies from the electrons coming from the carbon atoms in blue basically is slightly change their binding energy, but they remain near the initial value. We compare here the photoelectron spectrum taken at two pump probe delays, one before time zero at -200 femtosecond, which is shown with a dashed line, black dashed line, and another point taken at 100 femtoseconds, so after time zero, which is shown with a dotted line. And basically, it's the two photoelectron spectra are very similar. Indeed, small changes in the photoelectron spectra are expected since we expect to excite approximately 10% of the molecule. Nevertheless, here we can plot the difference of these two spectra, which is represented by a solid line. And we can observe, in particular, a clear depletion of the main peak at the energy E1. And this depletion can be ascribed to the C2 and C3 contribution in yellow, shifting to higher binding energy when we excite the molecule. At the same time, we observe a small increase of signal near to the energy E2 and a higher increase at the energy E3 that can be again attributed to how these electrons binding energy change after excitation. Indeed, at the energy E2, we have two contributions from the excited Rydberg molecule coming from the atoms in yellow, while we have only one contribution in the ground state. And at the energy E3, we have the contribution coming from the C1 atom, the red atom, from the excited Rydberg molecule. In the color map here, we show the photoelectron spectra at different pump probe delays, minus the one obtained at -200 femtosecond. And we still observe that this suppression of the main peak at the energy A1 lasts for all the pump probe delays that have been acquired, so up to 1 picosecond. And also we have that the increase of signal at E2 and E3 can be observed for all the pump probe delays, positive pump probe delays that have been acquired up to 1 picosecond. And well, this is in agreement, consistent with the lifetime of the excited Rydberg state, which has been measured to be approximately 3.3 picoseconds. In this plot, lineouts at these three energies are compared with a single exponential of 3.3 picosecond decay time, showing a fair agreement. We can now look at the PECD, and we can start again by comparing the two PCD measured at the two delays, minus 200 femtosecond and 100 femtosecond. We just show here the PCD in the region of energies where the measurement is reliable, and we observe a clear change of the PCD around energy E2. In particular, after excitation, PCD reduces in magnitude, going from approximately minus 18% to something around minus 10%. So we have an increase of the PECD, but the magnitude, the absolute value of the PECD reduces. So we try to answer to this question, why we observe this reduction of the magnitude of the PECD at this energy after excitation. And for explaining this observation, we can look at the PECD for the ground and the excited Rydberg state computed with CMS X alpha calculations. In these two plots, the PECD from each individual atom is shown with vertical sticks, and the total PECD is in black. And we can see that at the energy E2, the molecules in the ground state have only one electron contributing, that is the one from the C1 atom in red, and that has negative PECD. While in the excited 3s Rydberg state, there are two contributions coming from the C2 and C3 sides in yellow. And the mean PECD from these two contributions in this case is positive, so opposite in sign with respect to the one from the ground state molecule. So the observed decrease in magnitude of the PECD at E2 can be ascribed to the overlap of these two contributions, the positive PECD from the average contribution of C2 and C3, and the negative PECD of C1 from the molecules that are still in the ground state. And then we probed PECD at several pump probe delays. And we can observe that after the interaction with the visible pulse, PECD reduces in magnitude, and this reduction lasts for all the acquired pump probe delays up to 1 picosecond. We can use a simple model to compare our experimental data. And within this model, we assume that first, the observed PECD dynamics depends only on the relative population of the ground and excited molecules during time, while we assume that the PECD of these two states is fixed. And then we assume that we excite at maximum 10% of the molecules in the excited Rydberg state. And that this stayed the case with a 3.3 picosecond time constant. And the model here is represented by a dashed line, and it can explain the observed decrease in magnitude of the PECD at positive pump probe delays. So from a closer inspection, a dynamics on the picosecond time scale is also visible. This dynamics could be due to changes of the molecular geometry during the relaxation of the molecule that are expected to produce oscillations on the picosecond time scale, as was already observed from photoionization measurements from the valence Rydberg state. And or these dynamics could be also ascribed to the induced alignment from the visible pulse that has been neglected up to now. Obviously, further investigations are needed to confirm this picosecond dynamics, as the current confidence intervals do not allow to investigate these tiny variations. To conclude, and to summarize, we demonstrate PECD from core level using an FEL pulse and exploit this for the study of chiral dynamics of photoexcited Fenton molecule. This technique combined with theoretical calculations allow to unravel the role of different sites of the ground state and excited molecule in the total measure PECD. And in particular, we observed a change in the PECD that can be ascribed to the positive contribution of chiral sites C2 and C3 from a photoexcited Fenton. So this technique is expected to give new insight into complex ultrafast dynamics taking place in excited chiral molecules and could pave the way for answering questions related to the nature of chirality and chiral recognition. With this, I would like to thank you all and thank also the people involved in this experiment, in particular Caterina Vozzi, Michele De Vetta from the UDNI group where I work, Ivan Povis from the University of Nottingham that did the CMS X-alpha calculations, and Nick Besley for the TD-DFT calculations, who unfortunately recently died in a tragic accident. Our collaborators from Bordeaux and from Soleil, from Tokyo University, and the people from Fermi Trieste, our collaborator from CF Yale in Hamburg, and from CNRIFM in Rome. Thank you.
Thank you, Davide, for this presentation. And now the session is open for questions. And I really ask you for your help for asking questions to Davide, since he's worked with me. So I may ask questions, but it would be a bit weird. So while we wait for maybe some questions to pop up, what I can remind you is that you have to write your questions in the live question and answer. And despite what I told you before, you cannot really interact with us during the session, but at the end of the session, all the 3 speakers will be available in separate rooms for the open discussion in which you can talk with them for real. So they will be available at the end. I see. So there is a question from Francesca, who also participated in this work. Thanks, Davide, for the nice talk. Rydberg states are more delocalized and less sensitive to nuclear dynamics. I was wondering if you have considered the single photon excitation of some excited state leading to a strong nuclear signature on the PECD.
Okay, yes. This is basically something that we can also see from the theoretical calculations. If maybe I can go back to my slide shared here. Yes, it is indeed true, and we CMS X alpha calculations reproduce that that even if we excite an electron to a Rydberg state, the chirality of all the contributions don't sorry, this is the photoelectron spectrum. You have to go to the chirality here. As you can see here, for example, the yellow atoms do not change PECD after we excite the molecule in the excited Rydberg state. However, what changes is the binding energy of these 2 contributions. And that means that basically we can see these contributions that before were completely hidden and mixed with the ones coming from all the carbon atoms. But it is indeed true that also for the C1 atom that we cannot detect in the experiment because it's very weak when we go to the excited Rydberg state. Again, we have a PECD that is still negative on the order of 20%, both from the ground state and the excited Rydberg state. The second part of the question was, sorry, if we considered
a single photon excitation of some excited state.
Yeah, we considered it to obviously having a single photon excited, a single photon to excite our Rydberg state would be beneficial to be coherent with this excitation. Unfortunately, we didn't have the 200 nanometer light to single photon excite our excited Rydberg state, but it would be nice to use 200 nanometer light to directly excite the Rydberg state, so to be more sensitive.
Yeah, and not only the Rydberg state, Francesca is right, we may excite something, but one of the main, I would comment on this, of the main limitation that we have at the moment is the availability of pump sources for this kind of experiments, which is not very wide. But already at Fermi now they have 200 nanometer available. So yeah, it's improving. Okay, so there was a connection problem. I think the video got stuck for a little while, and so now we have Carlo commenting. I lost the answer due to the connection problem. Okay, but yes, it was prompting me to tell the audience that now we have 200 nanometer available at Fermi.
Yeah.
So they have it, and they are working for also getting short passes. So yeah. It's indeed, this is one of the main limitations, is that like you have to choose molecules that get excited with some wavelength which is available, that most of the time is like third or fourth, second, third or fourth harmonic of 800 nanometer. And it would be great to have like more flexible sources. And I know, as far as I know, these are getting ready for the next future in several FEL, but that Fermi already 200 nanometer is available. So let's see if we have other questions. Like, I hope now the connection is good. So Francesca is thanking for the answer. We have a couple of minutes more if there are other questions. Otherwise, we can move to the next speaker. Okay, so, well, thank you, Davide, again for the presentation and for the discussion, and talk to you later. And now I will introduce the last speaker of this section, Saba Fabri from MTA ELTE in Hungary, and it will discuss about quantum light-induced non-adiabatic phenomena in the absorption spectrum and quantum dynamics of polyatomic molecules. So, please, Saba, the stage is all yours.
Thank you very much for the introduction. Hopefully you can see my presentation and you can also hear me. All right, so today I'm going to talk about some recent results that have emerged from an international collaboration with these people. They are from Hungary, Germany, and France. Benjamin will actually present an invited talk in the next session, I believe. Okay, so what we want to do is to place molecules, shown here, into a nanocavity and study the interaction of these molecules with the quantized electromagnetic field of the cavity, which is represented by this green blob here in the middle. This is more like an artistic depiction of what's going on, but this is not science fiction, because such a setup is possible experimentally. And this kind of cavity experiments were done either with an ensemble or large number of molecules, or even with a single molecule. These are two respective examples here on the right. All right. So what do we have to know about molecules and cavities? Well, if we imagine that we place a single molecule in a cavity, then we have this Hamiltonian. This is a sum of the Hamiltonian of an isolated molecule, which depends on the nuclear and electronic degrees of freedom. And then we have the Hamiltonian of the cavity mode, which is basically a harmonic oscillator Hamiltonian with this angular frequency and creation and annihilation operators. And the third term describes the interaction of the cavity with the molecule, where this G is a coupling strength parameter, this is the molecular dipole polarization vector, and then we have the creation and annihilation operators again. We are going to focus on two-state molecules which means that we consider two electronic states of the molecule. And in this case, we can expand the eigenstates of the coupled molecule cavity system in the basis of the field-free molecular vibronic eigenstates multiplied by the Fock states of the cavity mode. If we use this expansion, and we can convert the previous Hamiltonian into this matrix form, where you have the low vibrational kinetic energy operator here on the diagonal, plus the potentials of the excited or of the ground or excited electronic states of the molecule, shifted by an integer numbers of the photon energy of the cavity. And in the off diagonal, we have some coupling terms between the different channels. All right. So the previous matrix corresponds to the so-called diabatic representation, where the coupling between the molecule and the cavity appears in the potential energy part of the Hamiltonian. Another way of describing this system is to use the so-called adiabatic representation, where we use a similarity transformation. We diagonalize this potential energy matrix, and this way the coupling is transformed into the kinetic energy part of the Hamiltonian. And if we use the so-called Born-Oppenheimer approximation, then we neglect these couplings between the different channels in the kinetic energy, and the Born-Oppenheimer approximation will be heavily used throughout my talk. What is really important to us now is the so-called singly excited subspace, which is represented by this two-dimensional matrix in this red box here. So in this case, the molecule is either in its excited state with 0 photon. This is what we call an excitonic situation, or the molecule is in its ground state and there is 1 photon in the cavity. This singly excited subspace accommodates the so-called lower and upper polyatomic surfaces, which can be seen here and here. And you can also see that they form a conical intersection, which will be important in the following. And again, these polyatomic states are hybrid light matter states, so they are superpositions of these two terms, at least to a good approximation. Molecule is ground state with 1 photon, and excited molecule with 0 photon in the cavity. All right. In order to test our ideas, we need a molecular system, which was suggested by Benjamin. This is formaldehyde, a 4-atomic molecule. Here you can see the equilibrium structure. This is a planar structure with C2V point group symmetry. And of course, this is a 4-atomic molecule, which means that it has 6 vibrational degrees of freedom. But in fact, it turns out that it is sufficient to treat the out-of-plane band mode, which is nu4, and the CO stretch vibrational mode, which is nu2, in order to get a physically correct description of the system, and we can omit the remaining 4 vibrational modes. So, like I said, we consider 2 electronic states. These are 2 singlet electronic states, a ground state X and an excited state A. Here you can see the respective one-dimensional potential energy cuts along the nu2 and nu4 vibrational modes. And I should also mention that the transition dipole moment between these 2 electronic states is 0 if the symmetry is of the given geometry is C2V. And that's the reason why we need to make displacements along the out-of-plane nu4 mode to get a non-zero transition dipole moment between the electronic states. So if we have a look at the field-free vibronic spectrum of formaldehyde, field-free means that the molecule is isolated, so it's not in a cavity at the moment. And we can do different computations. One of them is what we call the exact computation, which considers all the 6 vibrational modes of the molecule. Then you get the red spectrum. These transitions correspond, or these spectrum layers correspond to transitions from the vibrational ground state of the ground electronic state to different vibrational states of the excited electronic state. So if we drop 4 modes and keep only the CO stretch and out-of-plane modes, we get a 2-dimensional spectrum which is kind of similar to the 6-dimensional one. Of course, the spectrum lines are off from their exact counterparts, but the overall structure of the 2D spectrum is relatively similar to the exact spectrum. If we omit the CO stretch mode, so this way we get a one-dimensional model, we get these 3 spectrum lines, which is really different from the from the exact case. However, it is still useful to have a look at the one-dimensional results. So what we do here is that we compare the field-free one-dimensional vibronic spectrum to the case where we place the molecule in a cavity, and then we measure the spectrum of the coupled cavity molecule system. And as you can see, as we increase the coupling strength from G to 10G and 100G, the spectrum of the cavity molecule system changes gradually. Some peaks split and other peaks emerge, like here. And you can also notice that if we calculate the spectrum using the Born-Oppenheimer approximation, then we get something really different from the exact spectrum, except perhaps for the last case, where we can see that the spectrum contains 2 groups of peaks, and the Born-Oppenheimer approximation works for the first group, which can be seen here, and it breaks down for the second group of peaks. But why is this the case? Well, this question can be answered if we have a look at the potentials of the polyatomic potentials in the singly excited subspace. So if we increase the coupling strength, then you can observe that the structure of these polyatomic surfaces change drastically. For lower couplings, we have 2 light-induced avoided crossings here and here. And as the G increases, these 2 avoided crossings disappear and a single light-induced avoided crossing emerges here at Q equals 0. And if we have a look at the coordinate-dependent non-diabatic coupling curve, we can also notice that for this case, where we have 2 light-induced avoided crossings, the non-adiabatic coupling has 2 peaks that are symmetric to the Q equals 0. But if we increase the coupling strength, these 2 maxima disappear and a single maximum emerges here in the middle around this single light-induced avoided crossing. And I should also mention that in this case, you can see that the lower polyatonic surface has a wide and high barrier in the middle. Well, if we assign the spectrum, then we can see that these transitions correspond to final states, which are depicted here, 1, 2, 3, 4, and 5. So these are low-lying eigenstates of the lower polyatomic potential. And since we are somewhere here in energy, these states have 0 amplitude around Q equals 0, where the non-adiabatic coupling is large. And this answers why the Born-Oppenheimer approximation works for this first group of peaks. And once we reach the avoided crossing in energy, which is somewhere here, then the Born-Oppenheimer approximation is no longer valid and we get a completely different spectrum if we use the BOA or the exact methods. All right, so this kind of transition from a bimodal non-adiabatic coupling to a unimodal adiabatic coupling can be rationalized theoretically as well. I don't want to go into the details, but if you use the double harmonic approximation for this situation, then you can derive that the non-adiabatic coupling is proportional to 1 over G here and here, and it's proportional to G here in the middle. So what do we get if we have a look at the 2-dimensional spectra treating the nu2 and nu4 vibrational modes? Well, in this case, we can again compare the field-free spectrum to the cavity spectra with different coupling strength values. And as you can see, we can observe again the peak shifts and peak splittings and the emergence of new peaks. And for the highest coupling, we can again notice that the Born-Oppenheimer approximation works for the first group of peaks here, and it breaks down for a second group of peaks. And the reason why this happens is that we have a conical intersection between the lower and upper polaritons, which is highlighted here on the right. Of course, in this model, we have two vibrational degrees of freedom, so the polaritonic potentials can form light-induced conical intersection. And when we record the spectrum, we make transitions from here, from the ground state, to this region, to the singly excited subspace. And once we reach the energy of this conical intersection, then the Born-Oppenheimer approximation breaks down, as you can see again from this spectrum. All right. So in the second part, I would like to focus on dynamics instead of spectroscopy. And this part of my talk is inspired by a paper which was published by Feist and co-workers a year ago. This is the reference. I adapted these figures from their paper, and what they do is really nice and ingenious, in our opinion. So first they take a single molecule and they place it into a cavity. This is now a so-called lossy cavity, which means that the lifetime of the cavity mode is fairly low and the photon can escape from the cavity, so to say. And then they use a pump pass to transfer the population from the ground state to the singly excited subspace. In this case, they transfer population to the lower polariton. So this pump pass generates a non-stationary wave packet on the lower polariton, as you can see it here. And this wave packet will not stay there. This will oscillate back and forth in this one-dimensional potential, as you can imagine. And in the traditional way, of course, we would have to use a probe pass to track the motion of this wave packet. But instead of doing so, they suggested that we should have a look at the time-dependent radiative emission of the cavity. And why does it work and how does it work? Well, like I said, the polaritons have mixed hybrid or hybrid light matter characters. What does it mean? In the red region, which they call cavity, or we call it a photonic region, the molecule is in its ground state primarily, and there is one photon in the cavity. And in the blue region, which is called excitonic region, the molecule is excited and the cavity mode is not. So, and the wave packet oscillates between these two regions. And then, of course, we expect an efficient emission if the wave packet is here on the left in the photonic region. And when it moves to the excitonic region, then the emission drops down. And this phenomenon manifests in oscillations in this time-dependent emission curve. And this way you can follow or track the motion of the wave packet by recording this radiative emission signal. All right, so in this case, we have to deal with an open quantum system, which can no longer be described by the Schrödinger equation. Instead, we have to resort to the Lindblad master equation, which looks like an ordinary Liouville von Neumann equation supplemented with a term in the red box, which describes the incoherent decay of the cavity mode. And gamma c is the cavity decay rate, which determines the lifetime of the photon or of the cavity mode. So n is the number operator, rho is of course the density matrix. This is what represents the state of the system in this formalism. And what Feist did was to use this Hamiltonian, which can be seen here, to pump the cavity mode. So they couple a laser to the cavity mode, and then they identify the emission signal, which is proportional to the expectation value of the number operator, which can be obtained as an operator trace in our formalism. All right. So let's have a look at some own results. In the first case, we choose the parameters, the cavity parameters and the pump laser parameters in such a way that, that we pump the system from the ground state primarily up to the lower polariton. This is reflected by the populations. The blue curve is the lower polariton, and you can see that the length of the path is 15 femtoseconds. So the pump path ends somewhere here. And we transfer almost 20% of the population from the ground state to the lower polariton, and we do not transfer population, let's say, more than 2% to the upper polariton. And then if we have a look at the oscillations in the, or we have a look at the emission signal, we can see these oscillations in the green curve. This is due to wave packet motion between the photonic and excitonic regions of the lower polariton, as you can see here. So here we are at 15 femtosecond, right at the end of the path. The wave packet is localized in the photonic region. So we have an efficient emission. And then it moves to the excitonic region. This is the red region. And as a consequence, the emission drops down around 27 femtoseconds. So we have a local minimum. And then the wave packet moves back to the photonic region again, and then we have another local maximum, and then eventually the system relaxes into the ground state. So this is in analogy with what Feist and co-workers reported in their Nature Communications paper. Well, but we can do something else. We can also choose the cavity and laser pump parameters in such a way that we transfer the population primarily to the upper polariton and not to the lower polariton. And first, we decided to disregard the light-induced conical intersection between the lower and upper polaritons and see what happens in this case. So you can see from the populations that in this case, this brownish curve is the population of the upper polariton, and this is the end of the pulse. And the blue curve is the lower polariton population. It's 1% at most or so. So what happens in this case? Well, from the analysis of the numerical results, it turns out that in this case, the laser path generates a copy of the ground state on the upper polariton, which is more or less an eigenstate. So it won't really move, as you can see from these snapshots at 15, 30, 40, and 50 femtosecond. Like I said, in this case, we use the Born-Oppenheimer approximation, and we disregard the light-induced conical intersection. So the only change you can observe is that the norm of the wave packet decreases. And of course, that's the reason why you get an exponential decaying emission signal without any oscillations. But this can be rationalized by a simple theoretical model based on a two-state approximation. If you make this consideration, then you can solve the Lindblad-Master equation for this special case, and actually you can prove that we get an exponentially decaying emission signal. However, if the light-induced conical intersection is properly accounted for, or in other words, we take into account the non-adiabatic coupling between the upper and lower polaritons, we get something qualitatively different. Here you can see that the emission signal will show oscillations instead of this simple exponential decay. And the reason for this finding is that the light-induced conical intersection acts as a funnel between the upper and lower polaritons. As once we populate the upper polariton, this is the brown curve, this is the population, you can see that the population will drop down, and at the same time the lower polaritonic population will increase. And again, this is due to non-adiabatic population transfer between the photonic region of the UP and the excitonic region of the LP. And this is the reason also why, in this case, the emission signal strictly, or not strictly, but strongly follows the population of the upper polariton. Okay, so to sum up, I have shown you some examples in which we use the realistic description of a polyatomic molecule coupled to a single cavity mode. There is also, I should also mention that there is a single molecule in the cavity and not many molecules. First, we studied the absorption spectrum of formaldehyde, and we considered the field-free and rest cases. And these investigations revealed that you have to be very careful with these polyatomic potentials because they often form light-induced avoided crossings, or if you have at least 2 vibrational degrees of freedom, then you get light-induced conical intersections. And therefore, the Born-Oppenheimer approximation is of limited applicability. In the second part, I showed you that the ultrafast radiative emission can be used to track both wave packet motion on a single polyatonic surface and non-adiabatic population transfer between different polyatonic potentials. If you want to read more about the details, then please check out these papers, which are listed here. And with this, I would like to thank you for your attention and also thank the organizers for inviting me.
Thank you very much, Gustavo, for this talk. And now the session is open for questions. You can write your question in the live question and answer form. So we wait now for to see if somebody write down questions. In the meantime, I may start asking one question. Well, one question was, why did you choose formaldehyde?
Okay. This was originally suggested by Benjamin. He knows this system very well. And an important feature is that there is no natural non-adiabaticity in formaldehyde. And it's a 4-atomic molecule, so it's not too big, so it's amenable to high-level computations. And since there is no non-adiabatic, there is no natural non-adiabaticity in the molecule, you can be sure that if you get something non-adiabatic, then it's due to the field.
I see.
So it was an ideal system, we believe.
Okay, and yeah, when you were like at the beginning, you were showing the field-free modes of the molecule. If I'm not mistaken, those are all computed, right? Like theoretical calculation of the modes. And how do they compare with the experimental ones? Like, because you showed they are quite different, and then like the discussion go on with like the break of Born-Oppenheimer approximation. But it was curious to know, like with respect to something I'm more familiar with, like the standard vibrational spectrum.
Okay, so we have measurements for the field-free case, and you can find experimental values in papers, and they compare favorably.
But which one of the model? Because like the model were very different. This is what I mean, like you showed different models with quite different modes, right?
Yeah.
And so I just wanted to know is like which of the model like compare better with the, like, of course the exact I would expect.
The 6-dimensional, of course, yes.
Yeah, and so okay, and yeah, I mean, the second part of your talk was also very interesting about this possibility of, in polaritonic system, to study the dynamics of the molecules without really a probe. And I was just curious, I mean, like, this is really an experimentalist question. Which are the limitations on this approach that you can see? Even from the theoretical point of view, it's like, this is something that you can compute for, which are the requirements on the system that you can study?
Okay, so I cannot comment on the experimental aspects. I don't know if it's really realistic experimentally. Computationally, it's feasible. Absolutely. Of course, you have to pick a model that can correctly describe the physics.
Yeah, no, but I mean, like, which are the very strong assumption that you do for your, let's say, for your calculation that limit the system you can study with these, if there are? I mean, maybe it's very.
Well, of course, the size of the system can be limitation,
I see.
for example. But so for larger molecules, you can make approximations and select the vibrational modes which are really necessary. This is what we did here. We also did some 6-dimensional computations for the small system, not with the dynamics, with spectroscopy, so it's still feasible. But if you want to consider a larger molecule, then yeah, you have to make approximations, for sure.
Okay, well, thank you.
Thank you.
So we are perfectly in time, and we can probably move to the split session when where we can interact with the speaker of the session one by one. And well, first I would like to thank the 3 speakers of this session again, and all the people that attended the session. And then we move to the chat room, let's say, with the speakers. Thank you.